Now we are going to continue with Paweł, who is going to talk about how they won the Mercari Prize Suggestion Challenge. Okay, Paweł?
Okay, I have. Okay. Okay.
It's almost a classic here.
Yes, okay. Okay. Sorry for the unupdated date. I switched the presentation like 10 minutes ago because I talked too fast. And I have before a longer version of the same presentation. So we'll see a longer version of the same presentation. This is a presentation about the competition which took place 1 year ago. It started, I think, in December 2017 and ended 3 months later. And this is the team. The team was Konstantin. So you can remember Konstantin from previous slides. He was also a speaker on Kaggle Days Warsaw and Kaggle Days Paris. A very nice guy. And it's interesting because he's a software engineer, like by experience, and his data science experience is only 2 years long. Why I say this? Because I think that many good software engineers have kind of good start, can start very quickly in data science, because all they need to do is understand a few concepts. They can already program. So I think software engineers are quite good at data scientists. So it was very interesting how we won, because after 1 month of the competition, I was second in the competition and Konstantin was first. And we were switching places, like one time he was and the second time I was the first. So I thought to myself, I want to win this competition. And how do we win a competition? You team up with the best guy you can find. And in this case, it was Konstantin. I calculated that together we should be at least one place like more than alone. So I calculated that he should be more than 50% sure of his winning alone, not to accept my merging offer. So this was my idea behind why he should accept my offer to merge with him. So it was very good because, of course, we were very strong before. So after the merge, we kind of dominated this competition. I'm not being very honest here, but you can read the forums. People didn't understand how we got such good results. And the point of the competition was to predict the price of such an item. I mean, with only exception that we didn't have the photo. There were only a couple of columns that were related to description, title, and the category, and a couple of other columns like the state of the item, like whether it's used or not, and everything in between. Evaluation metric in this competition was very standard one. If you have problems that are regression problems, and prices can have multiple ranges, orders of magnitude, then it's a good way to solve this problem by using logarithmic scale. So the evaluation metric was root mean squared logarithmic error. It can sound a little bit complicated, but underneath it's just a very standard squared error metric. And to solve this using standard algorithms, you need to change the scale before solving this problem. Right? So you understand you have using a very standard regression model, but before you have to change the scale of target. I mean, everyone does it like this, so it's nothing new. So this is actually this is the standard. This is the raw price, and this is after applying the logarithm. So you can see already that it's a good way to solve this problem, because this chart is more like a Gaussian distribution, and this is what you want to see if you want to use models like this. This competition was very unusual for Kaggle because it was a code competition. Code competition is a competition when you don't submit the predictions, but you submit the script which runs on Kaggle servers and then runs for 1 hour and produces the results. So we can understand that I like this very much because it kind of solved some Kaggle problems. Kaggle problems is that towards the end of the competition, people start to merge together. And they kind of don't work together for whole competition, but only average their submissions at the end. And this is a problem because it doesn't encourage teamwork. Because it's very easy to just take a couple of submissions and calculate an average over submissions. So in this case, people that formed teams should have one code to create submissions. And this is what I liked about this competition, because I like to work in teams and I like to collaborate with people. So this competition kind of encouraged collaboration in teams. Of course, you had to create very fast models, and I will talk about this later. And there were some disadvantages of this type of competition. The first disadvantage was that this was, to some extent, a pure optimization problem. So you don't worry about the algorithm itself, you worry only about how fast it is. And you worry about the memory it takes to calculate. So there were many optimizations we took in order for our solution to work in this 1 hour limit. And there was also another problem with this competition, because in the second stage, the test set was 5 times bigger than in the first stage. So you can already see that people on the forums were not happy about this, because you have some standard 16 gigabytes of RAM, and then you have like 5 times more data. And what to do in such case? By the way, this solution of this problem is on GitHub. If you Google my GitHub, it's there, so you can read it later. Okay, so one thing we did right, I mean, there were many things we did right in this competition, but one of the things we did right in this competition was to create a kind of build system for our solution. Because the place to put the script in was this single window, right? So you had to create when I started to approach 1,000 lines of code in a single file, I started to kind of losing my mind because of this. So I decided to create a mini build system. So I created a script that used modules from Python, took all the files that consisted in this project, and then compressed them and unpacked in this one single script. So you can see that I could use modules, I could use separate files, and I put it down this kind of compressed system here. So I think it's kind of a hack, but it's a good hack. Because I don't think I abused this system too much. I think it's like the right way to abuse this kind of system. Okay, so this the data set was not complicated. It was about 1.5 million observations and only 6 columns, mostly text columns and categorical columns. Okay, this is how it looked like, raw observation. So it's very messy, and it had to be pre-processed surely to achieve good result. Also, another thing we, I think, did right was to use pipelines. I don't know how many people use pipelines in scikit-learn. Raise your hand. Oh, nice. When I say it's a good way, because you probably, if you don't use pipelines, you probably have like a very long script, and you declare classes, and you use those classes, and so on and so on. This is called spaghetti code in some circles. And one way to prevent this kind of messy code is to use this declarative approach and to create pipelines. It's very important because you can get a very maintainable code. Even in a 3-month competition, it matters how you can maintain the code. And it's also very easy to read and understand what's happening inside. So this is an example. It's a shortened version of the pipeline. So you can see all the pre-processing in one single place. So for categorical columns, I use one-hot encoding. For text columns, I use bag of words. And these kind of standard techniques to deal with this type of data. But it's very nice because it's in a single place. Okay. About the pre-processing, we used, I think there were not very much tricks here. One of the tricks was is at the end. It actually turned out that joining name and brand name and description was a very good idea, right? Because if you treat them separately, you get very sparse matrices with features. And when you combine those texts together, you get a lot denser like matrices with the more or less the same features. So there is no, I think also maybe you're not familiar that you can use n-grams of characters instead of whole words. It also helped a lot in this competition. And this is a slide that happens to show why you need to ensemble models in competitions. The first bar is performance of a single model, right? And you can see that using 4 is a kind of a good number for us because we had only 60 minutes. And we used, altogether we used 3 different data sets. So you take the same data and you apply 3 different pre-processing schemes, scenarios to the same data, and you get 3 different data sets. At first it was very obvious because I took my data set and I took Konstantin's data sets, right? So we had 2 data sets with 4 models each. So altogether at the beginning we had 8 models, and at the end we optimized the running times and we could afford to create additional data set. So we used 3 data sets with 3 models each. So altogether 12 models. And this chart shows how important it was to use 3 different data sets than only 1, right? Because, for example, if you use 4 models with 1 type of data set, you get this performance. And the best performance you get when you combine the 4 models with 3 different data sets. Because it's kind of interesting because people ask me, oh, how did you create 3 different data sets for the same problem? And I answer in this case is that you can pre-process the same data in different ways, because probably 2 people that are working like in this room or more, you would create hundreds of different pre-processing scenarios. And all of those things that you do are very important because the diversity matters when you take these models and merge them together. And this is a nice chart. It's very typical in competitions because it shows our progress in time. And I think it's very standard thing to see this staircase shape, because sometimes when you are stuck in a problem and you're kind of here and for a long time you don't improve, that means that you need to find another trick. Because a competition, winning competition is just finding the meaningful tricks that you can apply to the data so you can win the competition. And the more tricks you find, the better you are, right? I think this is also interesting because just to show you how much we kind of dominated the competition, we could finish the competition 1 month before the deadline. And it will be enough to win the competition. So I can also post this. We wasted 1 month of our lives, right? I mean, we couldn't know that it would be enough, but this is the same thing. We kind of 1 month before the deadline, we had enough advantage over the competition, so we didn't have to do anything. But of course we did, and we kept on improving the solution. Okay, so I had like 2-year break on Kaggle because this was in the time when deep learning started to dominate the scene. Like wherever you go, you can open a shelf and you see deep learning, right? And this was the case in my case, I was afraid. I was afraid that I didn't catch up to this deep learning stuff, so I don't know anything. And this competition proved to me wrong, because we applied some deep learning things and some of the things that were pretty standard. So if you think about the architecture, when you have text right now, you use some kind of recursive models like LSTMs, CNNs, and so on. CNNs are not recursive, but you know what I mean. You use just deep learning way of pre-processing the text. And what we did, we used a standard multi-layer perceptrons. It was kind of maybe it wasn't a trick, but it was very fast. These kind of models are quite fast, especially when they work on sparse matrices, right? Because there is a preconception that neural networks cannot work when you have 200,000 features. It's wrong. When most of those features are zeros, you can use sparse inputs, and then the neural networks are very fast. Actually, they are more or less the fastest way to train the models. Also, activation method. Activation was very standard for deep learning, so it's real. Optimization is also deep learning, because you can see the switch. Some of the things are deep learning, and some of the things are not deep learning. In this state of the art, maybe definition. And also, we didn't use embeddings for categorical features. We use one-hot encoding, so very standard thing. And this is the architecture. You probably like first page of deep learning page. The deep learning book is this kind of chart. So a basic, very standard multi-layer perceptron. And in this case, we thought that these kind of models are very good, because you can, when you estimate the price of products, you get a lot of interactions between features. So for example, if you have iPhone, it doesn't mean the same thing as iPhone and case in the same title of the item, right? And those interactions matter. And it turned out that we could use as many as 256 neurons in the second layer. So it's compared to deep learning approaches, the people who use deep learning architectures, like LSTMs, couldn't afford to train so many parameters in the same time. Oh, this is exactly what I was talking about. So you can have a lot of parameters, and it's much faster than creating all those deep learning architectures. Okay, and another thing worth mentioning is that Konstantin was our expert to train those models, and he noticed that he optimized the models so that they optimize the error metric on the second epoch, and they overfit on the third. So because many people can think, oh, it's overfitting, it's wrong. And actually, in case of many models, when you have a huge variance in the models, it's good that they overfit. Because altogether, they can, when you merge them, you can get a lot of better results. Like random forests. Each tree in random forest overfits to the data, and still, the random forest is a very good technique. So the same thing was here. This I can skip, okay. Some tricks that we used additionally was to use Huber loss. Huber loss is a kind of a loss. It's similar to squared loss, but it doesn't penalize very big errors. You can Google this later. And also, we used regression via classification. What it means is that we created 64 bins for prices, and we didn't predict the price itself, but with the bin of the price. And it also was a way to diversify the models, because the more diversified the models, the better the whole solution is. So it was a way to diversify our solution to create like another strategy to model. Okay, this is an example of Huber loss. So this is squared loss. So you can see that when the error is more than -1, it starts to explode, right? And this Huber loss is like a softer version of the same error metric. This is an example of binning. Actually, Konstantin used something like a soft binning. We didn't predict one bin, but we did predict the probability over a couple of bins. So, for example, this is the red color is one item. So you can see the predictions for this item are around this 3 price. 3 on the logarithmic scale. This is another trick we use because Konstantin liked this trick because he said it's the funniest trick he ever saw in a competition, because the competition was only 1 hour long. I mean, to train the models and to predict. You had to find cheap ways to transform the features. And one cheap way to transform the features was to take all the non-zero features and just convert them to 1. Right? So whatever you had in the matrix originally, like you can have TF IDFs or some counts that are not 1, you can convert them like all at once in the training to 1. So it was a way to kind of, again, diversify the training data, right? Because it's the recurring theme that you need to diversify the training data to achieve good ensembles. So this was a trick we used to diversify the data set. Okay, and we use, as I said before, we use sparse implementations of neural networks. So in TensorFlow, you have this kind of operator that takes a sparse matrix and multiplies it with a dense vector. So, and it's much faster than taking a dense matrix and multiply it by the same vector. It turned out that at the end, MXNet had the, sorry. At the end, we used MXNet because it was the fastest. We checked that it was the fastest, and also in the example later, we used just Keros in the code which Konstantin created. This is another thing that we did. It's pure optimization. It turned out that one model is much better trained on one single thread, right? And not that the model uses all 4 threads at the same time. So this is I mean, models that were trained individually on a single thread were like 2 times faster than a model that one single model that was using 4 threads at once. So this was a nice thing to discover. And this is also another trick we use. This is the setting you need to use so that each model can use only 1 thread. And as I have said, we did create an ensemble of 12 models. And these are the weights we found during the second stage of learning. So we used a very simple lasso regression to find those weights for all those models. And this is, you can already see that it's very balanced. I mean, there is no a single model here that is much better than other ones, right? And we spent a lot of time trying to optimize the parameters of those models. And it turned out it's almost impossible to optimize a single parameter in those 12 models. Because, and this is an example when someone tells me that he needs to optimize model parameters, right? You use grid search to find the best parameters. I always remember about this, because in the context of 12 models, those parameters of single models don't matter at all. So you can just train 12 models if you are able to do this, and just forget about this whole parameter search, because we found out that this parameter search for this kind of models don't work. Maybe in your case it can work, but in our case it didn't. Oh, this is exactly the thing I told you. So grid search didn't work. We tried very long to even improve our solution even more, but it wasn't very good. We also tried out a couple of different architectures in this problem. One of them was mixture of experts, but we didn't have enough success with them. And there's a very, very nice piece of code that Konstantin did at the end. I mean, after winning the competition, he created a single script that was about 80 lines of code. And this 80 lines of code would be enough to win the competition. So we can imagine when I tell you that a competition is also only like a series of tricks, then I mean it. This script compresses all those tricks in a single place, so we can see that it's not a lot of code. But to find all those tricks, it took our time. So you have, it's one of the, highest voted scripts, kind of on Kaggle, I think. You can see that all those tricks are explained. Here you do this feature engineering. When I told you that one of the tricks was to merge together name and the description, here you can see that it's done here, right? It can look like nothing, but it improved the results so much. So almost every line of code here is important. I mean, it should be. It's only 80 lines of code, right? Here you can see the definition of multi-layer perceptrons. And I mean, you can read this code if you want. It's very nice and elegant. Okay, we also kind of read the forums and saw what other people are using. Most of the people were using some kind of rich linear regression. Many people were stuck in this deep learning kind of architectures. I don't know if stuck is a good word, because they achieved quite good results with them. But I think our approach was better in this case. Also, one of the guys who took part in this competition created a small library that used factorization machines and this kind of novel kind of optimization scheme for neural networks. So a lot of people use this library, and also they did quite good in this competition. I know. You remember this guy, Nima? He won $1 million in this Zillow competition. So he was second in this competition. And they used a similar trick. They also combined together name and description, because it was a very important thing to do. And it's unsurprising that other teams have found this trick also. Also, they use sparse neural networks as we did. Also, third place solution use kind of convolutional neural network, and the second model was this model that was introduced in this competition. Okay. This is one of the tricks our competition used. Again, this is the thing that I was talking about. He used kind of Cartesian product of the features. So he used interactions between the brand name and some text from descriptions, and created manually those features. So he tested many combinations of those interactions, and he left the most important ones. Okay. So the main difference to our approach, we use only one type of model, the multi-layer perceptron. We did create 3 data sets, which was, I think, very important. And another thing that we did right was how we collaborated. We collaborated using a standard repository. We did create merge requests to our code. I mean, this is kind of good software engineering practices, I think. So every change that we did to our models was documented, and we knew exactly what we are changing and why. And we tracked each kind of merge request was tracking the performance of the models locally and also on the leaderboard. Okay, so this is all. Any questions?
Hi, Paweł. Thanks for the talk. Very nice. I have a question about embeddings. You were mentioning that one hot encoded performed way better than encodings. I'm curious about this since there were so many categories. If you look at Rosman competition, for example, the winning solution was basically categorical embeddings. So do you have any clue about why this was not the way to go in this case? Thank you.
I think that we didn't test adding embeddings to our solution because it kind of fitted how we created all those models. It was a very flat architecture without any any complications, if I can say. You had only one sparse matrix as input, and the multilayer perceptron did all the job correctly. So I think it would be wrong to kind of mess this simplicity, because I think it worked because it was so simple. And for this exact competition, the simplicity and how fast the solution was, I think I don't have any proof of this, but I think embeddings are maybe slower to train than sparse neural networks. So this probably was one of the reasons why we chose not to use those categorical embeddings. But it would be a nice idea for research if this would be, improve the solution.
Makes sense. Thank you.
Thank you, Paweł, for the talk. It was very interesting. Can you go back to one of the first slides where you have a bar plot regarding the number of models and the RMLSE?
This one or this one?
The next one. Yeah.
Okay.
So I didn't perfectly understand.
Okay.
Can you, for example, explain what the last two bars mean? And with this, I think we'll understand.
Okay, because here, these numbers represent the dataset versions you use. So if you're using only a single dataset, right? For example, the third dataset was the best one. And
stacking 4 models, or what does the 4 model thing mean?
Yeah, yes. I mean, you use free dataset number 3, and then you calculate 4 models on this. So here you have this undiversified solution. So you use only a single dataset. The second part of this is that you use combination of 2 datasets. Right? So any combination of 2 datasets is much better than a single dataset. And a combination of 3 datasets is the best. So this chart shows only that diversity of the datasets, even if you have the same number of models, matter. Right? It matters much more than the number of models. So I don't know if this is clear.
Yes. So the 4th bar means for the first model I did 4 models, and for the second dataset.
For example, here you have 3 models which use 3 ensembles which use 4 models each. If you ensemble together dataset number 3, you get this result. And if you ensemble 12 models, here you can see 3, 3, 3. This means that you use 12 models but with the same dataset. So you can see the difference. If you are using only a single dataset, you have this performance, and if you diversify your datasets, so your inputs, you get this kind of result. So, I mean, if you were in Kaggle Days Warsaw and on Giba Gilberto Titerich workshop, he would tell you that diversity is the way to win competitions, and this was a way to create diversified datasets. And diversified datasets was much more important than diversified models.
Okay, and another question. I'll profit the occasion. So you said grid search. You don't like it sometimes. Do you mean it's better to do ensemble of 12, no matter what hyperparameters models, and then ensemble done, find the best for one only model?
this is in a context, because in a context when you have some reasonable parameters, by reasonable parameters are parameters that you, for example, have an experience in. So you know that, okay, this is a reasonable number for, I don't know, learning rate. If you have those reasonable guesses about the parameters, then you can, of course, optimize them even more. But at some point, if you have an ensemble of a couple of models, tuning a single data set, model would be a waste of time. If you have some kind of reasonable parameters as the like first guess. I mean, you can try, but on your own. I mean, it's problem dependent, obviously, but I think I will remember this till the end of my life, that sometimes it's much better to just create more models than, yeah.
Hi, my question is about the metrics. You mentioned at the beginning that the competition was about root mean squared logarithmic error.
Yes.
But afterwards, you talk about Huber loss.
Okay.
The Huber is for training of the models before assembling, or
Yes.
when? Okay.
Yes. Yes. This Huber loss. I don't know where it is. Yes, here. It's an extension of, not an extension, but a kind of different version of squared error, because it's the same as squared error until this one threshold. Like from -1 till +1, it's the same as squared error, and beyond this is a linear. Like you can see it, a straight line. And it is important because in this competition there were a lot of outliers. And either you remove those outliers, right? This is one approach. We could remove those outliers. So there were items which cost like $2,000 and they had no description, right? It's impossible to train on such data set. So one thing you could do is just remove outliers, or the second thing would be to just use another kind of optimization metric in neural networks that allows these outliers not to ruin your whole model. So every time you have outliers, you can have both kind of solutions. Either change your data set to remove the outliers, or change your optimization scheme to allow outliers so they don't ruin your model.
Okay, so when you do the lasso for the final ensemble, do you use the Huber loss or the RMSLE?
Okay, so going back to this, sorry. It's a lot of slides, sorry. Going back to this, at the beginning you just convert everything to logarithmic scale.
Okay.
And only when you want to submit your predictions to Kaggle, you convert back to prices.
Okay, okay.
So we did also, this lasso was on logarithmic scale.
Okay.
I think I have a question. So I think you said that it's okay to put in ensemble some overfitted models, that it doesn't hurt that much. Like, can you elaborate a bit? What is the limit to that?
I mean, this is an idea that model which cannot overfit is too stupid to even memorize the data set, right? If the model is stupid, so it's very biased, then there is no sense of ensembling such models. So what would be, if you had like linear models, the extreme case, if you had linear models and you have 4 of them or 5, and if you ensemble them, you don't gain anything because all of them are linear, they don't overfit, they don't have any variance in them. So neural networks are models which can totally overfit to the training data, and this overfitting causes this kind of variance in the models. So the more variance you have, the more possibility to overfit. It means that your model has the capability to memorize the data, and also it can create a good ensemble. I mean, you can test on your own. If you don't believe me, just create a random forest with max depth of 2. right? If you have a maximum depth of 2, you create many very simple trees, and those simple trees are not good enough, not good enough to create a good ensemble because they don't have a huge variance. A huge variance in this case means that they are very sensitive to the input, right? If a model is sensitive to the input, it has huge variance, and then it can be used to ensemble, like in the decision trees, which are very deep, and you can ensemble them in random forests.
Understood. Thank you. Any more questions? Yeah.
Why using n-grams change your models? Why it's better?
You mean, I don't know. You mean a category character n-grams?
Yes.
Okay. This is what you were talking about?
Yes.
Okay. I don't know.
Because the second person after you use them. Use this.
Yeah, I think in this case, I consider this as a trick because it's not very standard way to pre-process text data and to use like characters instead of words. I think it was also in a context. We had 3 data sets, and this feature only worked in one data set. And at the time in the competition, we had 3 data sets, and each new idea was proposed to each data set. So after like 2 months into the competition, almost nothing new worked, except this one. I introduced this characters bag of words, and it improved only when introduced in a single data set out of those 3. Because it was, again, it created some diversity in our solution. So I think it worked because other data sets didn't have this kind of features. So.
Okay, thank you.
Okay, I think there are no more questions. Thanks a lot, Paweł.
Thank you.
There will be more time for you to ask Paweł during the networking time. Bueno, pues vamos a aprovechar este rato mientras que esperamos a las pizzas y os vamos a contar una propuesta que hicimos, que es que participemos todos en una competición de Kaggle. Vamos a sortear un Google Home Mini, creo, y hablarán nuestros sponsors y ya nos comemos las pizzas. Bueno, pues la otra vez propusimos un juego y era que nos apuntásemos todos a una competición de Kaggle, todos los que tengáis tiempo y os apetezca, ¿no? Lo estuvimos moviendo y tenemos un Slack y allí es donde se ha movido todo esto. Se ha propuesto una competición, es una competición de Microsoft, ya hay gente participando y os voy a contar un poco las reglas del juego que proponíamos. Vamos a ver. Y tras eso... bien. Bueno, pues se trata de que participemos todos los que somos miembros del Meetup, quien quiera y que haya asistido por lo menos a alguno de estos eventos. La idea es coger el leaderboard y empezar a quitar gente y cuando nos quedemos nosotros, pues el que esté más arriba ese ha ganado. No sé si conocéis cómo funciona Kaggle, pero tenéis un public leaderboard y un private leaderboard. El public leaderboard, digamos que a lo mejor es un 30% de las observaciones que estáis infiriendo. Y luego hay un 70% de observaciones, estoy poniendo un ejemplo, que enviáis a Kaggle
y no os da respuesta. El score que os va dando en el public leaderboard es respecto de este 30%. Pues cuando termina la competición, se vuelven a evaluar los modelos utilizando ese 70% del private leaderboard y se ven cambios. Por ejemplo, en este private leaderboard vemos que el que estaba segundo quedó tercero y al revés, ¿no? Pues esperaremos ese momento y quitaremos a los que no hayan asistido a ningún evento de Kaggle Days Meetup Madrid. Y luego seguiremos quitando gente. Vamos a quitar a los Grandmaster. No puede participar Pavel, no puede participar José Antonio Guerrero. Or in our private competition, we are not going to allow Grandmaster to play. Vamos a dejar a los Master, ¿eh? La idea es dejar a los Master. No pueden participar los organizadores del Meetup. Estaría feo, ¿no? Te has cargado a 3 Master. Pero sí vamos a dejar a los demás Master participar. Y, por ejemplo, así habría quedado, ¿no? Hemos puesto a uno joven, aunque sobradamente preparado, ganando. Pues podéis participar solos o podéis participar en equipos. Por ejemplo, podía haber cambiado el resultado si el tercero y el cuarto se hubieran juntado. ¡Pum! Esto de hacer equipos es más que recomendable. Os permite aprender de los demás, que es la parte más chula que hay, y podéis buscar gente que no sean de aquí. Es decir, si os aliáis con un Grandmaster, pues cojonudo, ¿sabes? Vamos, ahí nos hemos quitado nosotros al que queráis quitar. Esta es la competición que tenemos ahora en curso. Se han apuntado varios equipos, que ya está bastante bien para empezar. Es un problema, es una serie temporal. Yo no he buceado en los datos, pero viendo la descripción, se trata de coger observaciones de máquinas y ver si se van a infectar, qué probabilidad tienen de que se infecten con un malware. Y es curioso, ¿no? Tú puedes ver como una serie temporal, pues decir, vamos a ver en qué fecha salió el parche y cuánto tiempo pasa esta máquina sin actualizarse. Y cosas así, ¿no? Pues, tiene que estar curiosa. Ya queda poco, ¿eh? A esta le quedan... Vamos, ahora vamos a ver los tiempos. Bueno, ahora mismo ya hay 6 equipos de aquí participando. Estos que van primeros han estado a punto de colarse en el top 20. Para los que habéis participado alguna vez, para colarse en el top 20 no es fácil, ¿eh? Es complicado. Y me gusta que haya salido esta iniciativa y hayan estado a punto de colarse en el top 20. Ya tiene mérito, vamos. Y vale, esta competición tenéis hasta el 13 de marzo para completarla, pero una semana antes, el 6 de marzo, es la fecha en la que ya no podéis hacer equipos, es decir, podéis juntaros hasta el 6 de marzo, ni podéis iniciar la competición después del 6. Estas fechas están en todas las competiciones de Kaggle. Siempre tienes un entry deadline y un final submission deadline. Bueno, pues ya os he terminado de contar todo esto de la competición interna. Para el próximo Meetup ya tendremos un regalito para los que ganen y ya contado todo esto vamos a dejar a Javi que continúe.
Pues nada, antes de pasar a las pizzas y a la competición de Kahoot, descargaros la aplicación, el que quiera participar. Le dejamos 2 minutos a los sponsors. Creo que por parte de Innova tenemos a María. Le dejamos 2 minutos a los sponsors que nos cuenten algo sobre su empresa y hacemos lo de Kahoot. Gracias, María.
Hola, buenas tardes. Soy María Neira y vengo de Innova TSN, que he venido con unos cuantos compañeros que están por ahí. Este año, como habéis visto, somos patrocinadores del evento y nos gustaría serlo también en futuras ocasiones. Innova somos una empresa que llevamos 15 años trabajando, sobre todo especializados en el área de la analítica. Y pues llevamos diferentes iniciativas de vanguardia en empresas de diferentes sectores. el equipo de personas que formamos Innova pues está formado por gente de diferentes mundos. Gente más puramente matemática como yo o gente que viene de ingenierías, de economía. Entonces, creemos que esto es un aspecto muy, muy positivo porque hace que no nos quedemos solo en la teoría, sino que abarquemos y lleguemos al punto, o sea, al problema que estemos estudiando. Y bueno, eso, como he dicho, la pata principal de Innova es el mundo analítico. Entonces, todos los que estéis trabajando en cosas de Big Data y Machine Learning sabréis que esto es una continua formación y hay que estar desarrollándose continuamente. Y bueno, pues queremos participamos en concursos de estos porque creemos que es una motivación extra para seguir creciendo. Y bueno, estar hoy aquí también es una oportunidad para conocer gente y luego pues quien quiera puede hablar con nosotros porque buscamos también gente para que se una a nuestro equipo. Y nada, muchas gracias.
Muchas gracias, María. Ahí tenéis, luego dejaremos una diapositiva donde los sponsors han puesto un link porque están buscando data scientists, por si a alguno le interesa. Y teníamos también por aquí a Ricardo lo tenemos aquí, a Ricardo de Terminus 7.
Hola a todos, pues como os han dicho me llamo Ricardo Hortelano y vengo de parte de Intelligence, más concretamente del equipo de Terminus 7. En Intelligence es una empresa de desarrollo de software que tenemos oficinas, 2 aquí en Madrid, en Gran Vía y en Callao y otra en San Francisco. Y en Terminus somos el equipo de data, nos dedicamos a darle a empresas que lo necesitan soluciones de Machine Learning y de analítica de datos. Y nada, he venido a deciros que estamos buscando Data Scientists. También hay otros puestos en la empresa de DevOps y tal, pero bueno, supongo que aquí todos, si a alguien le interesa, será Data Scientist. Así que nada, ahora cuando en el networking, si os queréis, os acercáis a mí. Quedaos con mi cara si a alguno le interesa. Y nada, ya hablamos. Muchas gracias.
Muchas gracias, Ricardo. Y antes de pasar a las pizzas, por último, si queréis animaros a la competición de Kahoot, abrir la aplicación en el móvil. Vamos a poner ahí, son 10 preguntas, el que quede primero lo meteremos en nuestro hall de la fama y tendrá un detallito de parte de nuestros sponsors. Tenéis que poner, entráis en la aplicación del móvil, metéis el pin que aparece en pantalla. Esperemos que funcione, ¿eh? Esto es una prueba en directo, vamos a ver si con tanta gente funciona. Bueno, tenemos ahí unos cuantos ya. Sí, no solo es importante acertar la pregunta, sino que también es importante el tiempo que tardas en responderla, ¿vale? Las preguntas son un poco, os pongo antes, mientras, sobre Kaggle, sobre cultura general de Machine Learning, Deep Learning. Vamos, esperamos algunos segundos más todavía, a ver si se apunta alguien más. Ya somos 58. Ok, ¿alguien falta? ¿Todavía? ¿Alguien se ha ido? Vale, yo creo que ya está estable. Bueno, a ver si funciona, ¿eh? Ok. Preparados, ¿eh? Atentos. Saldrá la pregunta en la pantalla y hay 4 posibles respuestas. Pon el sonido. Ok. Ahí va. Pon el sonido de fondo si puedes, Daniel, del ordenador. Ok, 52 aciertos. Next. Albanahi va ganando. ¿Qué empresa no es Gold Sponsor en este evento? Ok, next. Charco va primero. Fernando, tú no puedes participar. Vamos. Ok. Esto fue aquí. No, el 30 de octubre aquí en Madrid tuvimos a José Antonio Guerrero. Next. ¿Con qué asociáis la imagen que aparece circulada de las tres? Ok, 48. Next. A ver. Jorge Santiago. Hombre. Vamos a por la siguiente. ¿Quién ha ganado más medallas de oro en Kaggle? Uno. Gilberto. Señor. Best Fitting es el número 1 actualmente, pero Gilberto es el que más medallas de oro ha ganado. Vamos a por la siguiente. Steiner va ganando, Jorge segundo, Sheriff tercero, Álvaro cuarto. François Cholet es el autor principal de... Keras. Vamos a ver quién va número 1. Next. Steiner, Sheriff, Álvaro. Ok, next. ¿Quiénes son los dos autores del paper de XGBoost? Ok, Tianqi Chen, yeah, y Carlos Gestrin. A ver quién va. Steiner, muy bien. Vamos, no sé si queda la última, a ver cuál va. O la octava. ¿Por qué algoritmo es conocido Ian Woodfellow? Por las GANs. Ok. Vamos a ver quién va. Primero, dale. Sheriff. Ok. Vamos a por la penúltima, ¿no? La novena. ¿Qué tipo de red neuronal sería más adecuada para clasificar imágenes? Ok, Convolutional Neural Networks. Next. Ok. LRL, nuevo en el leaderboard. Sheriff segundo. Steiner tercero. Ojo que el tiempo es importante y es la última pregunta. Adelante. Next. ¿De qué función de activación se trata? Relu, correcto. Y el ganador es LRL. ¿Quién es por ahí? Un aplauso. A nuestro primer ganador de la prueba Kahoot. Segundo, Sheriff. Tercero, Steiner. Solo tenemos un regalito. Un aplauso al ganador. Bueno, y con esto nos despedimos y pasamos al que quiera tomarse una pizza o una cerveza. Nos vemos arriba. Muchas gracias a todos, ¿eh?